Assalamu alaikum everyone. Welcome to the course of Real-Time Embedded System, and this is our lecture number 6, and in this chapter we're going to discuss the design methodology of embedded system. We're going to see what are the design steps that we have to take, what are the approaches. We will define an example. With the help of that example, we will show how we can build a complete embedded system. So let's start it. Okay folks, so before we move to our current topic of design methodology or design technology, we will start with the recap of what we have studied in our previous lecture. So more and more physical things will be augmented or embedded system with computing. Things will become smarter. Computing system will be present in every system. And we have stated that an embedded system is a system that is embedded with programmable computer for specific application of that system. And the question arises, why embedded system? Because they are more flexible and have simpler development. And with the passage of time, physical things will be equipped with embedded system. As we have seen, things will become smarter, and computing system will be present in every electronic devices. We have also seen that embedded system is a system other than desktop computer, and that's the basic definition of the embedded system. And embedded system is like tightly constrained. It is single function. It is real-time and reactive. That is why we prefer embedded system over a desktop computer when we have to perform specific tasks. So let's move to our today's topic, that is of design methodology. So design methodology is a procedure for designing a system. Now you have to understand your methodology helps you ensure you did not skip anything. Software engineering tools are required, which includes CAD tools and etc. These tools can help you automate methodology steps, keep track of your methodology itself. Now, design technology involves the manner in which you convert your concept of desired system functionality into implementation. You must not design the implementation to optimize design metric, but you must do so quickly. The designer must be able to produce large number of transistors every year to keep pace with IC technology. Hence, improving design technology to enhance productivity has been a key focus of software and hardware design communities for decades. To understand how to improve design process, let's move on to next slide. So in design methodology, we have to achieve these 5 goals. Number 1 is performance. Performance is related with speed and deadline to meet the requirement, like you need to develop a system in that amount of time. Functionality and user interface, you need to take care of what are the functionality that the system need to provide. The user interface, the cost of manufacturing should be low, power consumption should be low, and other physical requirements like size and other design metrics need to be optimized. So these are the 5 goals that you need to look when designing a system. Let's move on to next slide. So in this slide you can see that we have like 5 levels of abstraction. We have requirement, specification, architecture, component design, system integration. We define everything at very abstract level. For example, in requirement we tell what sort of functionality is required. In specification we specify something in quantitative way. In architecture we choose some architecture like x86, like 8086, like some other architecture, ARM. In component design we design those components like at gate level. At system integration we integrate all the system to make our design complete. Now moving on to next slide. So usually the level of abstraction is two-way. Like we can have a top-down approach or we can have a bottom-up approach. In top-down design, we start from most abstract description So it is your requirements, and then we work towards the detail, like towards component, towards architecture, and this is our top-down design. Whereas in bottom-up design, we work from small components, like we start from the component integration, we work with the gates, and then we go towards our top side. Whereas real design uses both techniques, like you can move between top down and bottom up approaches. Okay, let's move to next slide. So when designing a system, we required refinement at each level of abstraction. At each level of abstraction, you must need to analyze, refine, and verify. You need to analyze the design to determine how can we meet specification. You are specified with the specification, so at every level of abstraction, that is requirement, specification, architecture, component integration, and component design, you need to analyze how you can meet these specification and refine the design to add detail. You can refine your design to add more detail to it, and at each level of abstraction you can verify that either you are on track to meet the design goals or not. So refinement is required at each step. Moving on to next slide. Now let's take an example of designing a system. Suppose you have a product idea, and the product idea is to develop a device that can record for each day the number of stairs that the user has climbed up or down. So we need to design a system that counts the number of stairs climbed by the user either up or down. From this number, you can calculate the amount of carbon dioxide saved and calories burned. Okay, so let's call this device stair counter. So the question is how to start from here. So just a while ago we have seen that the typical design flow is like this. We have requirements. Requirements is followed by specification. Specification is followed by architecture. Architecture is followed by component development, system integration. So now this is top-down design. We're moving from requirement to specification, architecture, component development, and system integration. You can also go from system integration all the way towards requirement. This is bottom up design, and as I have told you, real design often iterative. You can move from requirement, and from requirement you can go to specification. If for example you think that requirements are like that you cannot specify them, or you cannot use this particular architecture, you go back and re-specify or edit the requirements. Moving on to, so starting with the requirements. Requirements are usually described in native language or plain language. Plain language description of what the user wants and expect to get. So we define in native language like what is the requirement and what user expect from us. For example, as I've just told you, the example is to develop a device that can record for each day the number of stairs that the user has climbed up and down, and on the basis of these steps that he has climbed up or down, we want to know the amount of carbon dioxide saved and calories burned. Describe how the end product is used by user. May be developed in several ways. So the requirement may be development like what are the requirements. This can be developed either by talking to customers directly or talking to market representative, or we can make a prototype and give it to user, and then later on the user can comment on the product, like for example this thing is missing, so the requirement needs to be added, or if something is extra, like they do not need it, we can take out this requirement. Okay, so moving on to next slide, that is all. Oops. So there is one more slide of requirements. So often need to know target customers and business models. So like requirement also depends like what is your targeted audience. Like are you going to make it for some layman or you're going to make it for some expert person? So like stair counter can be as an add-on in your cell phone. For example, like you have seen many apps. You can track your activity, you can track your calories burned, you can track your heart rate. Just like that, you can have stair counter in your cell phone. So like if it's a requirement that it is needed to be in cell phone, so that's a requirement. You can have a consumer product, as you can see here. It's a consumer product, it is in cell phone. And like finally you can have a gift. So depending upon the requirement, we can alter the shape of the stair counter. Okay, so but these are not limited, we can have another form as well. So moving on to next slide. So basically there are two types of requirements that we need to address. Number one is functional requirement and number two is non-functional requirement. The functional requirement includes internal as a black box and describe only the output as a function of input. So we don't know like what's in the black box, we only care about the inputs and we only care about the outputs. So functional requirements are described in the way what are the inputs, what operation will be performed, we are not care about this, but what will be the output. So show number of stairs climbed up or down. So that is like our output. Show amount of CO2 saved, that is our output. Do not count in other cases. So like we do not need to count in other cases. For example, if a person is walking on a flat road, if he is not climbing, we do not need to count. Okay, and what about like non-functional requirement? So non-functional requirement are kind of a design metrics: performance, reliability, size, weight, power, cost, and so on. Okay, so usually when designing a system there is a form called requirements form. We define the name of the system, that is in our case a stair counter. Now we define purpose, like what we need to do: count and show stair climbed and CO2 saved. We need to specify inputs. Input is power either on or off, so that's just a simple toggle button. Outputs, we need LCD to show these amount of or the number of stairs climbed and CO2 saved. Performance, update every step. So this is kind of a performance that we need. And manufacturing cost will be around $150. So we need to like make a rough guess like how much amount is it's going to be. The total number of power consumed will be around 100 milliwatt, and physical size and weight will be 2 into 3 inches and 4 ounce. So these are the requirements, like we cannot go beyond this physical size and weight, we cannot exceed the power of 100 milliwatt, we cannot increase the manufacturing cost, and we have to meet the performance, that is like update on every step. Okay, so moving on to next abstract level, that is specification. In specification we get more precise. Usually we define the specification description in quantitative way, okay, like a number. In this specification we should not imply a particular architecture, like which architecture we are going to use. We do not talk about that, we do not discuss anything about the architecture, we just specify something in number form. We list some assumptions. For example, we need to update the screen after 0.25 seconds after each step or user interface, for example, etc. Now, specification may include functional and non-functional elements, may be described in unified modeling language. So there are tools that are there to specify the system requirements. So we can use these unified model language or other than that. Okay, moving on to next slide. So there are two things in design methodology. Number one is what, which we have already seen in requirement abstraction. Number two is how, which we will see now in architecture design. So in architecture design, we need to specify like what component satisfy the specification, need to know what are available. So in these we talk about or we discuss hardware components. So for example, what kind of CPU, peripherals, for example, if we are going to use MS430 CPU and 3-axis accelerometer, what software component we are going to use, major programs and their operation, for example, software for accelerometer, software for LCD driver, and so on, must take into account functional and non-functional specifications. So you can see that at every stage at requirement, we are looking at the functional requirements as well as non-functional requirements. At Similarly, in specification, we were looking at the functional specification and as well as the non-functional specification. So we have to take into account the functional and non-functional specification at architecture design. It means like if we are going to use that MSP430, is it going to be a low power? Is it going to be cost effective? Is it going to be performance oriented or not? So we need to take account into all these specifications, functional or non-functional. So once we are done with the architectural selection, we move on to component development and actual implementation of individual hardware which we have selected and software components. We must spend time architecting the system before you start coding. Okay, some components are ready-made, some can be modified from existing design, other can be designed from the scratch. So it depends upon what component you are going to use. Some are already built in, providing the existing functionality, or you can make them from scratch. For example, you can already use some existing hardware MSP430 3-axis accelerometer and then you can program it. Okay, or you can make a board like MSP430 from scratch. So you can also do some sort of surveys in order to find out like what kind of component you need to use, like for hardware or for software, and that will definitely help you out. So moving on to final step of design methodology is system integration in top to bottom approach. Now in system integration, we put down all the components. At this stage during integration, many bugs will appear. You need to have good interface definition from start. You need to have a plan how to integrate the components so that you will be able to uncover the bugs quickly. Test as much as functionality as early as possible. So as we have talked about, like you need three refinements: analyze, then you have refine, and then you have testing. So testing and verification is very important at every stage. So as long as you have a good plan for integration of the components, you can uncover the bugs quickly and easily. Moving on to next slide. So as of now, I hope that everybody has like good idea of what is like requirement, what is specification, and what is architecture. So now we will look into the system development of a state counter, like how to proceed to develop the components and integrate systems. So we will look into the hardware and we will look into the software, like what is going to be our programming environment, and what is going to be our real hardware. Okay. So development environment typically consists of two things. Number one is host, as you can see here. We have a computer, that is host, and then we have a target system, that is our actual device. So host, a computer running program tools for development. For example, you might have worked in big microcontroller, you might have worked in Key, you might have worked in C language. So in host computer you use some programming tool for development purpose. In target, the hardware on which the code will run. So you can think of it as a microcontroller on which your code will run. After program is written, compiled, assembled and linked, it is transferred to the target. So we use a host computer to write a program, we compile it, we debug it, we assemble, and then we transfer it to the target. So in previous slide there was a acronym ARM. So ARM stands for Advanced Risk Machine. That was your target machine. So the host computer was using cross compiler in order to convert its instruction for the target environment. So in development process is a process for creating instructions that are built on host but meant for target. So on your right side you can see that either we can work in C or C++, or if we have assembly files, then obviously we need cross assembler, otherwise we need cross compiler. You can see here there is a difference. Here we have cross compiler and here we have cross assembler. Then cross compiler will create object files and cross assembler will also create object file. Then we will use some sort of linker and locator to combine these, and then we have an executable version that will be run on the target. So tools are compatible with each other. There is a tool chain. In tool chain we have compiler, we have assembler, we have library and linker. Okay, so we have compiler, this compiler, then we have this linker and locator. Okay, so this is the development process. Now let's talk about what are like linkers and locators for computers. We are talking about computers here. Linkers. Linker creates an image file to be run on the host. So for example, if you have x86 computer, so what linker is going to do? Linker is going to create an image file that is going to be run on that particular system. What loader does? Loader loads image into memory during runtime. Okay, so loader loads that image during runtime. Whereas for embedded system, now if we talk about embedded system, linker creates an image file to be run on the target. Okay, so linkers are on both sides. They are on computer side as well as on the embedded system side. So linkers create an image to be run on host as well as linker create an image to be run on target for both. Whereas locator create a file containing the binary image or other format that will be copied on the target, which run on its own, not through loader. So in embedded system we do not require a loader. It's a locator that creates a file containing the binary image or other format that will be copied onto target, which run on its own. It needs exact addresses beforehand. Now, certain parts of program need in ROM and some parts need in RAM. Normally done by dividing segments. We divide the program segments into ROM and RAM parts. Some needs to be run in ROM, some needs to be run in RAM. Now, locator needs to be told where in memory to place segments. So we need to tell locator like where in memory we need to place these segments. Either is it in ROM or is it in RAM? Okay. So that was pretty much about the design methodology. Now coming off to summary, development of a system involves, as you know, that requirement, specification, architecture, component development, system integration, test and validation. We have seen that once requirement, specification, architecture and design is finalized, how we can choose components and how we can do system integration with the help of cross compiler, linkers, locator, which fall under tool chain of a development environment of a embedded system often includes development host with tool chain, cross compiler, linker, locator, library, emulator. Emulator basically is your software that is used with the development board. Okay, so this is something that is already in your course book, but there are few changes over there. If you go and look, there will be system specification, behavioral specification, RT specification and logic specification. Alongside this, you will have compilation synthesis, libraries, test and verification. Please go through that portion as well. I have already discussed that thing in your class, and please, um, our chapter number 1 is almost finished, so please go through all the things that I have discussed here in slides as well as in class, and inshallah from next lecture we will start chapter number 2, which is about the designing of a single purpose processor. Allah Hafiz.